Hi, so in this set of videos we're going to look at logarithms and we're going to work with logarithms. Now, I had thought about doing this whole set of episodes in a Scottish accent, but I thought no, that'd just be just a bit cheesy, and anyway my Scottish accent's not that good. Why a Scottish accent, I ask you? You ask. Well, there is a reason for that, and the reason is this chap over here. So bring him across. A rather dour looking Scotsman by the name of John Napier. He was the 8th Laird of Murchison. Means he was a Scottish nobleman. Among other things, he was also a mathematician. At that time, one of the big problems that they had when dealing with working with maths and problems around that were mathematical was how we went about calculating really big numbers or difficult numbers. And this is what perplexed and confounded Murchison and things and what he wanted to work on. Now, he worked on this little premise. If I go and take, say, a simple little calculation like this, 8 times 16, well, we can do that in a number of different ways. We can use the old-fashioned algorithm and say 6 eighths are 48, and then 8 tens are 80, and I add the two together and I get 128. That's fine. I can do that as long multiplication. But if I went and gave you a different calculation, say a calculation of 32 times 128, well, then we're starting to look at a slightly longer multiplication. And yeah, it's doable, but it takes time. Now, Napier had a look at this and said, well, 8, I can write 8 in a slightly different way. I can write that as 2 to the power 3. And 16, I can write that as 2 to the power 4. Now, with the work that you did last year, you'd be able to look at those two and say, hang on, I've got the same base. And so when I multiply those two things together, I'm going to get 2 to the power 7. I've got 3 2's tied up in the first one, I've got 4 2's tied up in the second part. So in total, I've got 7 2's being multiplied together. And in fact, 2 to the power 7 is 128. So this problem that I have down below here could be made a whole lot easier if I think of 32 as 2 to the power 5 times by 128, which you've just seen is 2 to the power 7. And when I multiply that together, I'm going to get 2 to the power 12. And so I can come up with an answer that's written as an exponent, 2 to the power of 12. Now, this number over here, this 2, is referred to as the base. This number over here is the exponent. And those two words are going to be important, and we're going to look at them in a little bit more detail as this video progresses. So Napier was looking at a way in which he could try and simplify the process of multiplying and dividing numbers. And I know this shows my age, but when I was your age at school, we didn't have calculators and we had to use log tables in order to do these sorts of calculations. Now, that's for another discussion another time. The other thing that they looked at was how you went about dealing with exponential equations. What is an exponential equation, you ask? Well, an exponential equation looks something like this. So if I've got 2 to the x is equal to 256. The variable, the thing that I don't know, is up here in the exponent. Now, this is a fairly simple equation because 256 is just double 128. So this is in fact 2 to the power 8. So 2 to the power x is equal to 2 to the power 8. In other words, x must be 8. That's easy enough to do. If I had 3 to the x minus 1 was equal to 243. Again, this is the sort of thing that you'd have dealt with last year. 243, you'd have told me, is 3 to the power 5. And so 3 to the x minus 1 is equal to 3 to the power 5. In other words, I can say x minus 1 equals 5, and so x is equal to 6. That's all good and well, but what happens if I have something like this? 3 to the x minus 1 is equal to, not 300, is equal to 242. Well, that's not 3 to the power 5. It's some number to a power. It's 3 to some power, but we don't know what that power is. And this is what Napier was able to help with his work on logs. Now, his initial work on logarithms was groundbreaking, but not a finished article. It was later added to and refined by later mathematicians, but Napier is the one that is credited with setting up the notion of a log. So let's look at a definition of a log. Here's what Mr. Google has to say about it, and I think this is as good a definition of anything. A quantity, a logarithm, is a quantity representing the power to which a fixed number, the base, must be raised to produce a given number. A log is a quantity representing the power to which a fixed number, the base, must be raised in order to produce a given number. So in other words, if I wanted to make the number 1000 and I was working with a base of 10, what is the power that I must raise this number to? What is the power I must raise 10 to in order to get it to 1000? Now you should be able to see that fairly easily, that that's going to be the number 3. So I can rewrite this in a slightly different way, and I can say the logarithm to the base 10 of the number 1000 is equal to 3. That is, 3 is the power that I must raise 10 to in order to get 1000. So if I want to generalize this, I can say the following. Let's get this in black. So if a to the x is equal to b, then log to the base a of b is going to equal x. And that is critical to our understanding of logs. There is a connection between an exponent form over here and a log form over here, and we're going to have to switch between these two, switch between the exponent form and the log form. So we've got to understand that these two things are connected, and when we come to look at the graphs of logs in a little while, another video shortly, you will see how these two things are connected. Now, there are a couple of important definitions or ideas that we need to pick up to begin with. And that is this. Here's the first one. If I've got log to the base a of 1, what am I going to get? Well, if we think about this in terms of, not in the log form, but in terms of the exponent form, my base is a. I want to get the number 1. So what is the power that I must raise that to? Well, it must be the power 0, mustn't it? So the log to the base a of 1 is always going to be 0. So that's the first sort of definition point that we need to consider. There's a second one that we need to consider as well, and that is, if I've got log to the base a of some number a, what is that going to equal? Well, again, if we go and think of it in terms of exponentials, an exponential form, I've got a, I want to raise it to some power, and I want to get the number a at the end. So what is the power that I must raise this to? This obviously has to be the power 1. And so log a of a is going to equal 1. Those are two really important basic things that go with the definition of a log. Graphs coming up next. See you then.